Hello students, in this video we're going to just do a little bit more with the cross product and determinants and see that there's some relationships between determinants and areas and volumes in 2 space and 3 space respectively. So just remember from our previous work that the determinant of a 2 by 2 matrix A, B, C, D, first, second row, might be denoted by one of these two notations, where either we just use DET and put the matrix inside that parentheses to represent the determinant. We also will see in textbooks and videos that we have the vertical bar notation and no brackets on the matrix, and just put the numbers inside there. The determinant's defined by AD minus BC. Again, the way we compute that is we multiply the main diagonal, think about that with a plus sign, and then multiply the off diagonal, think about that with an associated minus sign, and then compute that number. That number can come out to be 0, positive, or negative. Alright, now we're going to get to some facts about 2 by 2 determinants and how they're related to areas in 2 space, and then we'll also see how 3 by 3 determinants are related to volumes in 3 space. So we're assuming that U and V are non-zero and non-parallel vectors in 2 space. Alright, non-zero, non-parallel will mean that those two vectors do not lie in the same line through the origin if we were plotting them in standard position. We're going to denote by the matrix, the 2 by 2 matrix, when we put U and V in there, we mean the 2 by 2 matrix with the components of U in the first row and the components of V in the second row. Here's one fact, and then we'll have a fact after that related to the area. But it's saying if U and V are non-zero, non-parallel vectors in 2 space, this also works in 3 space, then sums of scalar multiples of U and V, and by that we mean we're taking a scalar, multiplying it by U, a scalar multiplying it by V, and then adding those results. Okay, if we take all of the sums of scalar multiples, which we call linear combinations, for those constants being between 0 and 1, then that determines or spans a parallelogram. Again, we call sums of scalar multiples of given vectors linear combinations. So what we're saying there is if we look at any combination C1 times U plus C2 times V, and if those numbers C1 and C2 are between 0 and 1, and we look at all such possibilities, that's going to determine a parallelogram. Let's look at the picture here. Let's assume that we have the vector U is pictured as such and V is pictured as such. What happens if we add U and V together? Well, what we would do by that is take the vector V and redraw that with out at the tip of the vector U. Okay, so redraw that vector. All right, so that's redrawing V based at the tip of U, and then we would then draw the vector U also at the tip of V, and that determines it's supposed to be a parallelogram. I'm a little short on my length there, but that's what it would be like if we had C1 and C2 to both be 1. We would get the vector going all the way out from the origin to there. We would get this point. What would happen if we would take, for instance, let's just do an example, half of V and add that on to 1/2 of U. Alright, well, either way we do this, maybe we'll start with half of V and add on half of U, and then we would get to going from the origin to the tip of that vector. What we're thinking about is we're at this point. Alright, so we can think about vectors as points when convenient and also as vectors. What we're saying is we can get to any point inside this parallelogram or on the boundary of it by choosing appropriate numbers C1 and C2. And hopefully that's fairly obvious. Alright, and if I want to get to this point, I'm going to have to go a little bit out the vector V, and then in the direction of the vector V, and then a certain amount in the direction of the vector U. Okay, so we can see that 2 vectors that are non-zero and non-parallel will determine a unique parallelogram in 2 space or in 3 space. All right, now here is the fact that we're going to use and practice a little bit with. If we have 2 vectors, U and V, and I've got them in components as A and B for U and C and D for V, then the area of the parallelogram spanned by those two vectors is given by the absolute value of the determinant of the matrix you get by putting the components of U in the first row and the components of V in the second row. Okay, you could switch that up. It doesn't matter which row the components of U and V go in, because you're taking the absolute value in the end. But this is kind of surprising. It shows that 2 by 2 determinants have something to do with area in two-dimensional space. Later we're going to show that 3 by 3 determinants have something to do with volume in three-dimensional space. All right, so we're just going to do a couple examples with fact 2 on the next page, and then we're going to move on to 3 by 3 determinants. Okay. All right, so here is the next couple examples that I would like to work out with you. So I'm saying, all right, find the area of the parallelogram determined by these two vectors, U and V. Let's draw the picture for this first one. I'll sketch it down. All right, so suppose we put an X, Y axis down. U is 2, 3, so over 2, up 3. Let's assume this is the vector U. All right, V is negative 1, 4, left 1, up 4. So there's the vector V. And what we're saying is, if I think about the parallelogram determined with these as its sides, something like that, that this area of this parallelogram will be the absolute value of the determinant of the matrix we get by putting the components of U and the components of V in a matrix, taking the determinant, and afterwards taking the absolute value. All right, so that area is going to be the determinant, the absolute value of the determinant of the matrix we get by putting components of U, which are 2 and 3, in the first row, components of V, which are negative 1 and 4, in the second row, and then computing that determinant, and afterwards taking the absolute value. So again, we're going to multiply the main diagonal, which is 2 times 4, so it gives us 8. I'll just put 2 times 4 minus the product of the off diagonal, so in this case, negative 1 times 3. So we get the absolute value of 8 minus negative 3. So in this case, we get 8 plus 3, absolute value of 11, which is 11. Okay, and we could do a very similar thing for the second example in there. For time's sake, we'll just move on. But again, this fact shows that the area, the determinant of the matrix you get by putting the components of one vector in the first row and the other in the second row has a relationship to area, which is kind of surprising given the determinant is just an algebraic quantity. All right. Now let's move on to three-space vectors and volumes. All right, so this is just a definition I've taken out of the OpenStax book, and you'll see this in pretty much any calculus book you pick up. The scalar triple product, or triple scalar product, excuse me, of three vectors, and we're assuming this is in 3 space because the cross product only makes sense for vectors in 3 space, is given by this quantity here. So U dotted with V cross W. All right, now the next result says that scalar triple product, or triple scalar product, is equivalent to computing a 3 by 3 matrix. And what we mean by that is that this matrix right here, the determinant of this matrix, it's the determinant of the matrix you get by putting the components of U in the first row, the components of V in the second row, and the components of W in the third row. All right, and that's equivalent to doing separately the cross product of V and W and taking the dot product of that with U. All right, let's just investigate that for a moment. All right, so let's just investigate that and just show that that's true. To compute a 3 by 3 determinant, we do cofactor expansion across the first row. All right, and so just remind ourselves how to do that. We're going to multiply U1 by what we get by crossing off the first row and first column. So this quantity here is U1 times the resulting 2 by 2 determinant we get, which is V2. We're left with V2, V3, and W2, W3. And then we get minus what we get by taking the middle row, crossing that out with the first column, and that would be U2 times the resulting 2 by 2 matrix would be V1 and V3, W1 and W3, plus the third component of the first row, which is U3, and then cross out that row, first column, we'd be left with a 2 by 2 matrix, and multiply it by that determinant, V2, V1, V2, and W1, W2. And what you should notice in here is that these are the components here, this including the minus sign, and this, those are the components of the cross product. Alright, so that's kind of just a quick derivation of that formula. Alright, we're going to get to some examples on the next page, and a result showing how that's related to volumes. Okay, again, I've taken this out of the OpenStax textbook, and you'll see this result in pretty much any textbook you look at. But what it's saying is that the volume of the parallelogram, which is the three-dimensional parallelogram, as I've got one pictured down below here. This figure came out of the OpenStax book. So say you have three non-zero, non-parallel, and three vectors that don't lie in the same plane in three-dimensional space. Those determine a unique parallelogram, which is referred to as a parallel pipette in three-dimensional space. What we're saying here then is that the volume of this three-dimensional parallelogram here is equal to the absolute value of the triple scalar product. And by our previous result, that's the absolute value of the determinant of the matrix you get by plugging the components of U in the first row, the components of V in the second row, and the components of W in the third row. And then computing the determinant and taking this absolute value. So I want to do an example by computing that, and that will be it for this video. Alright, so the example we have is the one listed down below. It's saying compute the triple scalar product. I want to think about this as the volume of the parallel pipette determined by these vectors with sides A, B, and C respectively. Alright, so I'm going to do it as it's shown here by doing the cross product of B and C and then dotting that with A. Alright, so I wrote down what the cross product is. Remember, we put I, J, K across the first row, and then the components of B and C in the second and third row respectively. And then what we get is the 2 by 2 determinant by crossing off the first row and first column, and then multiplying the vector I by the determinant of that resulting 2 by 2 matrix. Alright, so it's going to be 3, -1, -3, 3 times the vector I. And then we get minus the 2 by 2 determinant we get by crossing off the first row and middle row, middle column, first row, and that's giving us 0, -1, 5, 3 times the vector J, and then it's plus the 2 by 2 determinant of the 2 by 2 matrix you get by crossing off the last column in first row, which is 0, 3, 5, -3, and that's times the vector K. Okay, sometimes what I like to do is just go underneath this matrix and put a component down here, and then look above and cross it out. So we're going to get 9 minus +3, so that's going to be 6 in the first row, and that's going to be the opposite of what we get by looking above, crossing out that middle column. We're going to get 0 minus -5, which is going to be +5. But then we have to negate that, and then what we get by crossing off the last column, that's going to be 0 minus 15, so -15. Alright, so our vector is 6, -5, -15. That's B cross C. Alright, now to do the volume obtained of the parallel pipette or the parallelogram, what we're going to do is the absolute value of A dotted with the vector B cross C. Alright, so we're going to take the absolute value of what we get by taking the vector A, writing those components down. We get 2, -4, +1, dotted with what we just came up with, 6, -5, -15. Computing that dot product and then taking the absolute value. So the absolute value of 12 plus -4 times 5 is 20, plus 1 times -15 is -15. So it will be the absolute value of 35 minus 15, which is going to come out to 20 after we take the absolute value. So that will be the volume of the parallel pipette determined by those vectors A, B, and C.